This video is binomial and geometric distributions. So our learning target is I can model and solve problems using binomial and geometric distributions. Okay, so these first two questions are just what do you think will happen? So you just read through them, write down an answer as long as it's a coherent thought, actual sentences. I can tell that you actually put some brain power into it, you'll get credit. Alright, so let's look at what binomial experiments and distributions are. So those two questions that you answered occurred in a binomial setting, which means that there were two possible outcomes. So that's where you're getting binomial from. In a binomial experiment, here are your requirements. So each observation is going to fall into one of two categories. It's either going to be a success or a failure. There are repeated trials of the experiment, because remember, just doing an experiment one time doesn't mean anything. You have to do it multiple times. There is a fixed number of observations, and we're going to use the letter N to represent that fixed number of observations. The N observations are independent, so they don't influence each other anytime. And then the probability of success, which we'll use the letter P for, is the same for each observation. Another thing I didn't put is anytime we use the letter Q, that's going to represent a failure. So N is your number of observations, P is your probability of success, and Q is going to be your probability of failure. So let's think about this example. If you flip a coin 4 times and you count the number of times the coin lands on tails, this is a binomial experiment. Why? Because there are repeated trials. There are 4 coin flips. Each trial can only have one outcome. It either lands on heads or lands on tails. The probability of success is constant, so 0.5 every time. And the trials are independent, so the outcome of one toss does not affect the outcome of the next toss. So that's just how you would prove to me that you had a binomial experiment. You'd be looking for these categories right here. So it's kind of like a checklist. Alright, so let's decide if these are binomial or not. So I want you to try it. I want you to pause the video and see if yes, it's binomial and tell me why, or no, it's not binomial and tell me why. Try that in 1, 2, 3. Alright, so both of these are binomial because both of them are completely random. The probability is consistent throughout. There are independent trials and there's only one outcome. So this is very wordy, but over to the right, binomial probability. The probability that an n-trial binomial experiment results in exactly x successes when the probability of success on an individual trial is p. Okay, so an example. Suppose we flip a coin 2 times and count the number of tails. So that's going to be our successes, how many times it lands on tails. The binomial random variable is the number of heads, which can take on values of 0, 1, and 2. Alright, so I've listed what can happen when you flip a coin twice. So, number of tails occurs 1 out of 4 times, which is 0.25. The number of tails landed just one time would be 2 out of 4, which is 0.5. And then the number of times tails occurs twice, which would be 1 out of 4. Okay. So here's the notation, and this is what you're going to use every time when you do these type of problems. So every time we use the letter N, we're talking about the number of trials in the binomial experiment. Whenever we say P, the probability of success on just one trial. Q is going to be the probability of failure, but you can always find it by doing 1 minus whatever P was. And X is the number of successes that result from the binomial experiment. Alright, so let me show you this crazy formula, because I have to. I'm sorry. Oh, it's really crazy. So to find the probability of success of an individual trial is P and is calculated. Here we go. Ooh. That is a doozy. When we did it, so sometimes you'll see like it in a different format, but they all mean the same thing. Okay, And then here is some stuff that we've already talked about. So variance and standard deviation. And I'm going to show you what those formulas look like. Alright, so here's variance. You would do n times p times 1 minus p. And for standard deviation, you would take the square root of that. Alright, so now we're going to try it. So big scary formula, I know, but we're going to try it. So a die is tossed 3 times. What is the probability of 1, 5 showing up? So n is your number of trials. It's tossed 3 times, so n is going to be 3. X is how many times, the number of successes that result from it. So what's the probability of 1, 5 showing up? So 1, it only happens 1 time. And then P is going to be your probability of success. So if you're tossing a die, remember it's a 6-sided die, so it's going to be 1 out of 6. Okay, so now we're going to put it into that big scary formula. So it looks like this. I'm just going to fill in. So on top, it's going to be n factorial, and that's a button in the calculator, over 1 factorial, 3 minus 1 factorial. 1/6 to the first power times 5 over 6 to the 3 minus 1 power. We're going to put all this in our calculator. Alright. If you don't know how to do that in your calculator, you need to message me or watch the video that I did on how to put in a factorial. Alright, and then we're going to do the next one the same way. So hospital records show that patients suffering from a certain disease, 75% die of it. What is the probability that of 6 randomly selected patients, they will recover? So we need to know what n is, what x is, and what p is. Okay, so n is the number of it's the number of trials, and you're talking about 6 because you're looking at 6 people. X is your number of successes that result from it. So our x is going to be 4. And I got 4 because if you think about 75%, so that's 3 out of 4. So 4 is going to be how many successes I have. So by P, if 75% die, then that means 25% live. Alright, so 4, 6, 0.25. So we'll put them in the formula. So 6 factorial, and I'm just reading the formula. And then times 0.25 to the 4th power, 0.75 to the 6 minus 4th power. Put that all in your calculator, and you get this big, huge number. So it's a big, scary formula, but I'm not going to expect you to memorize it or anything. So as long as you know what numbers to plug in and what they mean, and then you know the buttons on the calculator, you should be fine. Okay, so let's do some other stuff. Alright, so for each example that you get to, this is what you do. First, you're going to read it. A card is selected from a standard deck and replaced. This experiment is repeated 5 times. What is the probability of selecting 3 hearts? Step 1, you want to identify each part, just like we did in those last examples. You need the trial, which is drawing a card from the deck and replacing. You need to know what the success rate is, drawing a heart. The failure rate is not drawing a heart. And then you're going to identify the letters. So n is the number of trials you have. So it says it is repeated 5 times. So n is 5. P is your probability of success. So you want to draw a card from a deck, and it's a heart. there are 13 hearts in a standard deck of 52 cards. So that's actually 0.25%. Q is your failure, probability of failure, which is always 1 minus whatever P was. So it's going to be 0.75. And then X is your number of successful times. So if you want it to draw out a heart and you're going to do it 3 times, X is 3. Alright. So first you got to read it and you got to figure out what your trial, success, and failure are. And then step 2, you got to figure out what N, P, Q, and X are. And then the last step, we're going to use the formula to solve. Okay. So here's what it will look like. 5 factorial over 3 factorial times 5 minus 3 factorial. It's a minus. 0.25 to the third power. 0.75 to the second power. You can do these in steps or you can do it all at one time, but you get this number. Okay, so what I want you to do is I want you to see if you can do this for A and B. So I want you to pause the video and really try it, and then we'll go over it. So try it in 1, 2, 3. Alright, so you can see how I set it up. And then you just put it in your calculator and it spits out a number. Alright, so try C, D, and E the same way. Follow those steps. See if you can pick out the right pieces, and then I'll go over them. So try it in 1, 2, 3. Alright, so I gave you answers for C and E, and then I worked out D. If you have any questions, you can ask me about them. It's a big, scary formula. It's just calculator steps, and I don't know, it can be confusing, so let me know if you have any questions. Okay, so let's say we want to know the chance that a basketball player will make his 3rd free throw. I don't care about any of this, but maybe somebody in the world does. We know that the probability that he will make his free throw is 0.6. So what's the probability of missing the first 2 and then making the 3rd throw? So he misses, which is 0.4. He misses again, 0.4. And then he gets the last one, 0.6. If I multiply that all together, this is what I get. Alright? And then what would be the probability of missing the first 3 and then making the 4th? So he misses, 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 and then makes it. Alright. So let's see if we can find a pattern. So find the probability for 5, 6, 7 throws and then complete the table. So do it exactly like I just did and see if you can complete the table. And then answer this question, what pattern do you see? And there's a lot of different patterns, so you can really just come up with your own answer. But try to fill out the table, pause the video, and actually do it in 1, 2, 3. Okay, so this is what I got for the table. For what pattern do you see? The numbers are going down. Whatever you see. As long as you put something down, it's a coherent thought, you're good. Alright, so let's talk about geometric distributions. You may have noticed the geometric sequence in the probability above. This is why geometric distributions are called geometric. A geometric distribution represents the probability of failure. Probability of failure. So let's look at our example from above. And when we talk about K, we're talking about the number of shots the basketball player takes before making a basket. So in notation, we can think of this as the probability that X equals K equals the probability first K minus 1 trials are failures, and then the last trial is a success. So that's exactly what we did. Or, here's the big complicated formula. So it's going to be P, then 1 minus P in parentheses, to the power of K minus 1. Also remember that 1 minus P can also be written as Q, like we talked about earlier. So Another way to write the formula would look like this. So P and then Q to the power of K minus 1. Alright, so a little bit easier formula, but you have to understand when to use binomial and when to use geometric. Okay, so let's do some examples. So let's say you want to find the first person from a polling station that voted for an independent. Success is voting for an independent candidate, and then failure would be not voting for an independent candidate. The probability of voting for an independent candidate is 0.2. You poll each person as they leave the building to find out who they're voting for. So what's the probability of finding an independent after interviewing 5 people? So we need to figure out what K equals, what P equals, and what Q equals. Alright, so remember that K is the number you went through before you had that first success. And P is your success, and then Q is going to be your failure. So read through this and see if you can figure out what the numbers will be. You can try that in 1, 2, 3. Okay, so for our example, K is going to be 5. So you had to interview 5 people before you found an independent. So that's why K is 5. P is the probability of success, so 0.2. And then failure would be 1 minus 0.2, which is 0.8. Alright, so now we're just going to use our formula, and then we're just going to plug it in. So here's what ours looks like. So 0.2 goes here, then 0.8 to the 5 minus 1 power. You put that in your calculator and get 0.8192, and that's your answer. Alright, so then if we change the question to what's the probability of finding an independent after interviewing 15 people, K is now 15. The probability of success is 0.2. Failure is still 0.8. So all we do is we would change the number to 15. So it would be 0.2 times 0.8 to the 15 minus 1 power. And just like in that first table that we did, we should expect a much smaller number, and that's what we get. Yeah, it's really not that bad. You have to be able to understand the difference between binomial and geometric. So let's just make sure we understand how to determine between them. So binomial has a fixed number of trials before the experiment begins, and X counts the number of successes. Alright, geometric has a fixed number of successes, 1, and the first, like to do something, and it counts the number of trials needed to obtain that first success. So that's the difference between them. Alright, so an example of binomial: if a family decides to have 5 children, then the number of girls, which are your successes in the family, has a binomial distribution, because you're either going to be a boy or girl. Geometric: if the family decides to have children until they have the first girl and then stop, then the number of children in the family has a geometric distribution. Okay, and then I'm going to write out the formula differences so you can see those as well. Okay, so remember, standard deviation is represented by sigma. That's that little symbol. Variance is sigma squared. And those are your formulas for binomial and geometric. Pause the video if you need more time, but I'm going to keep moving on. Alright, so we're just going to do some examples. Alright, so here's some types of questions I might ask on a quiz or a test. You select 20 cards from a standard deck of 52 cards. Let Y be the number of diamonds selected in the 20 cards. Which of the following best describes the situation? So I want you to read through them and see if you can pick out the best answer. Try that in 1, 2, 3. Okay, so this would actually be C. It's a binomial distribution, and it's 20 observations. The probability of success would be 0.25. Yeah. So that's how you would do a problem like that. Number 2, in order for the random variable x to have a geometric distribution, which of the following conditions must x satisfy? 1, p has to equal 0.5. 2, the number of trials is fixed. 3, the trials are independent. 4, the probability of success has to be the same for each trial. So which one works for a geometric distribution? Try that in 1, 2, 3. Okay, so the only ones we talked for geometric are these last three, so 3 and 4. So my answer choice would be E. In order to be geometric, the trials have to be independent. The probability of success has to be the same for each trial. The number of trials is definitely not fixed, and the probability of success doesn't have to be 0.5. Alright, so number 3. Roll one 6-sided die 8 times. The probability of getting exactly 3 ones in those 8 rolls is given by the following. See if you can pick out the correct one in 1, 2, 3. This one, D, is your correct answer. If you have any questions about that, you can ask me. But those are the types of questions I would ask you, not to do that whole entire long process, because I think it's a lot. Alright, let me know if I can help.